Okay, I wanted to make a video to get you guys ready for tomorrow. So let's talk about these patterns and recursive and explicit equations. And then at the top it just says, remember, recursive equations have two parts, the starting place and the pattern where to go next. Explicit equations will likely come from finding the areas. Be sure to show on the diagram how you set up your area equations. Okay. So number one, type the equation for the quadratic function in the box, and then you have to show how you develop your equation on the diagram. If you don't do that, you don't get credit, so make sure to do that. Verify your equation works. Okay, so I actually have the answer key up right now, so let me switch to student view. Okay, you could probably see what it was there, but let's talk about how to do it. So for this one, let's do the recursive first, and then we can go ahead and talk about how to do the explicit, okay? And you just need to be able to demonstrate that you can do that, on at least one of them. So what I'm going to do for the recursive is I'm going to make a table, which is going to go 1 and 5 and 2 and 8, 3, and how much is that one? 13. Okay. And x and f of x. And so when we do the recursive, we need to think about the first difference and the second difference. So my first difference, when I go from 5 to 8, is 3. Now, after meeting with many of you, you seem to really understand what's going on for the most part, but you're writing that 3 in the wrong spot, and then it's throwing the entire problem off. So when I go from 5 to 8 and it goes up 3, I need to write that 3 right next to the 8, okay? I don't want to write it up by the 5, okay? That's just something that you need to kind of remember. Just another thing that you need to remember. And then when I go from 8 to 13, that goes up 5. And when I write that 5, I write it next to the bottom number. So I write it right there, okay? And since I know that this one is quadratic, I know that it's going to be going up 2. And then since it's quadratic, I know that the second difference, this is all going to be 2, which means that my first difference is climbing by 2. So like this would be 7, okay? So if that's 7, the next one, I would add 7 to the 13 for 20. And then I would work backwards in the other direction. This would be like a 1, right? Because that row is going up 2. So my recursive equation we talked about how it is plus the linear equation of the first difference. Okay, so I'll say that again because it's the most important thing that I've said yet. It's the linear equation of the first difference. So I don't have my highlighter pen, but this is my first difference row. Okay, so it's going 1, 3, 5, 7. I need a linear equation for that. So a linear equation, remember, goes y equals mx plus b of the first difference. So m is the rate of change. What's the rate of change for the first difference row? Because it's different for each one, right? I'm talking about first difference. It's 2, right? Because it's going 1, 3, 5, 7. Okay, and then I need the b of the first difference row. So I know that b is the start value, which is across from 0. Okay, so this is going down 2. I would have -1 right there. Okay, so a common mistake is to write whatever goes here. That doesn't matter, okay, because we're looking at the numbers in the first difference column or row. We're getting the b from what's across from 0. Okay, and the m is what's going on each time. So it's f of x equals f of x minus 1 plus 2x minus 1. And that is the answer for the recursive. And then to fully get a 4, I'm going to have to give a reference point and just say like f of 1 is, well, what was f of 1? F of 1 is 5. Or I could have said f of 3 is 13, just kind of giving me a starting place, okay? All right, to verify that it works, you could, if you want to, like if I wanted f of 4, for example, that means I would plug in 4 for all my x values. And what's 4 minus 1? It's 3. And plus 2 times 4 minus 1 is 7. Okay, so now f of 4 is equal to f of 3. What is f of 3? F of 3 is 13. So I put in 13 plus 7. And then I have now proven that f of 4 is 20, which is true. Okay, so there is a good 4 for a recursive. All right, now let's talk about the explicit. I need to erase all of this. So as I do my erasing here for the explicit, start to look at the pattern of how it's growing, okay? What things are always there staying the same? And then what's the thing that's actually like changing each time? So I know that these are consistent. They don't change, and they're always there. Okay, so if I were to have like figure 0, that's all I would have is those 4. So the only thing that's changing is this. So we want to start thinking, what's the relationship between that thing that's changing and the figure number? So for figure 1, it's a little 1 by 1. For figure 2, it's a 2 by 2. And then I start thinking, okay, well, what's the base and the height of it? Like, how wide is this 1? It's 1. How tall is it? It's 1. And then this one, this is 3, and this is 3, and this is 2, and this is 2. So how would I get the area of any one of those shapes? And remember, we think of that as x, right? The figure number is x, okay? So if that's x, what would the height be? The height is also x, okay? Because it matches, like it's 2 and 2. So the area of any one of those is x times x. So f of x for the explicit is equal to, I would go x times x, and that gets me the area of this, okay? And then I would have to add the 4 that are always there. So f of x is equal to x squared plus 4. And then I would just want to test that. Let me erase this because it's really marked up, to make sure that that is correct. So for example, 3, I have how many? I had, was it 13? There's 13. So when I plug in 3 here, I better get 13. Let's see. So f of 3 is equal to 3 squared plus 4. And yeah, 3 squared is 9, and 9 plus 4 is 13. And there's the proof for it. Okay, number 2. Type the equation for this quadratic in the function box, or in the answer box. Show how you develop your equation on the diagram to justify your equation. So again, you need all these things that I'm writing down, like you have to show your work. Okay, you can't just type the equation. Verify your equation works by using one of the known values. That also shows me that you know what you're talking about for this, okay? Okay, so for this one, I'm going to start with recursive again. And I have day 1, I have day 2, and I have day 3. And day 1 looks like it has 4. Day 2 looks like it has, let me just add up here real quick, it looks like it has 9. And day 3, let's see, that's 3, 6, plus 4 is 10, 13, 15, and 16. You might pause the video and see if you can get the recursive on your own. So just like the last problem, it is no different. I'm going to build out first difference and second difference. So when I go from 4 to 9, I add 5. Now think about where you're going to write that 5, because I said it was very important in the last one, okay? I'm going to write that 5 next to the 9, the bottom number, okay? And when I go from 9 to 16, that's 7, I'm going to write it down by the 16. Knowing that it's quadratic, I know that this is coming up 2, and that all of these will be 2, and that this is linear, okay? So for me to get the recursive equation, I would have to do f of x is equal to f of x minus 1 plus, do you remember? It's the linear equation of this first difference column, okay? So how is that, what's the slope of the first difference column? What's happening there? It's adding 2, right? Because this would be like 3. So I know that it's 2x, because that's the rate of change in my first difference column, plus, and then whatever is across from 0 in the first difference column. So here is 0, and then I would just go over, and what would go there? Well, if it's going up by 2, this would be a 1, and it'd be 2x plus 1. Okay. Hopefully that made sense to everybody, okay? All right, for the explicit, I'm not gonna make you do the explicit for this one, but if you wanted to go ahead and try to figure it out, you certainly could, okay? But this video can only be so long. The main ones that I want to do the explicit for are the ones that are all connected like that, like number 1 or number 2, or or number 3. Okay, type the equation, same set of instructions. Okay, so for this one, for the recursive, I'm going to make my table. How many? 12? 3 is going to be 20. Is that 27? Yeah, it's 27. Okay. This one's a little bit bigger, but the rules don't change. So from 3 to 12, I'm going to get 9. And from 12 to 27, I'm going to get 15. So I know that this must be 6, which would give me 21 here, and would give me 3 right there. So my recursive equation is f of x is equal to f of x minus 1 plus the linear equation of the first difference column. Same thing over and over again. So what's the rate of change in the first difference column? It's not 2 this time. It's finally something different. It's going up 6 each time. It's going 3, 9, 15, 21. So this is going to be 6x plus whatever is across from 0, the y-intercept of, so if I have 0 here, I don't have much room. What would go right over there? Well, it'd be 6 fewer than 3. So it'd be negative 3. So this would be plus negative 3, or I would just write 6x minus 3. And then just to prove that it works, I'm not going to do this every single time, but just because the video can only be so long. But if I were to plug in 3 to this equation, I want to be sure that it works, because that's how I check my work, and that's how you show me that you know what you're talking about, okay? So f of 3 is equal to f of 2, because 3 minus 1 is 2, plus, what's 6 times 3 minus 3? That's 15. So f of 3 must equal f of 2. What is f of 2? How many blocks are in f of 2? it's 12. Okay, 12 plus 15. And is it true that f of 3 is 12 plus 15? Were there 27 blocks? There were. And I have now proven it. That's the recursive. Okay, now for the explicit equation. Okay, for the explicit equation, we are going to have... Okay, start looking at the figure number and think about how it relates to the base and the height, okay? So in figure 1, I see that the base is 1. In figure 2, I see the base is 2. In figure 3, I see that the base is 3. So that means that it's equal, okay? So it's x, because the figure number matches the base. And then I start thinking about the height. So is the height also 1? No. The height is more. So I might start thinking that it is x plus 2, okay? Because this, I can tell here that the height is 2 more than the figure number. The problem with this is that when I go to number 2, I try to do that again. So I'm like, okay, well, maybe it's okay, it's figure 2, so it'd be here, and then plus 2 would only get me to here. So my rule isn't consistent, and it didn't work. And a lot of you guys can probably already spot what's really going on here. What's really going on here is when I relate the figure number and the height, I'm like, okay, when it's 1, it's 3. When it's 2, it's 6 high. When it's 3, it is 9 high. So what's my relationship? It's not adding 2 each time, okay? You can probably spot that it's triple, okay? When it's 1, it's 3. When it's 2, it's 6 high. When it's 3, it's 9 high, okay? So really, the height of any one of these is triple, okay? Is triple the figure number. So it's going to be, it's 3x high. So now if I wanted the area of any one of these, I would go x, the base, times the height, which is 3x. And what is x times 3x? It's 3x squared. And just to prove that that works, I'm going to plug in 3. So f of 3 is equal to 3 times 3 squared. 3 squared is 9, and 9 times 3 is 27. Okay, I think I'm going to make this video 1 and have it be the one that I show in class. And then video 2 will be one you can watch on your own if you're struggling and you need help preparing for the test.